sharing stuff.
Okay, so it looks like the recording is in progress. So maybe we should get started. Let me get started by introducing the speakers. So our boss Ian said that we will have two speakers today who will speak for half an hour each. And then after that, we'll have a dedicated discussion session, perhaps of another half an hour. So let me first introduce the speaker, the first speaker, Subhash Singha. He's a scientist right now at the Quark Matter Research Center of the Institute of Modern Physics, Chinese Academy of Science in Lanzhou, China. He had been on a number of positions. First, as the chief scientist. He started as the senior research fellow at the Variable Energy Cyclotron Center in Calcutta, India. And then he was a senior research fellow with the National Institute of Science, Education and Research in India as well. More recently, he was a visiting researcher at the CERN, and also visiting researcher at INFN Catania, Italy. And later on, he was a guest researcher at the Brookhaven National Lab, and also postdoc research associate at Kent State University. In I think 2019, he joined the Institute of Modern Physics in China in Lanzhou. So he had been working on the many things, I guess. More recently, he had been working on the spin polarization and spin alignment measurements with the star at the Relativity Heavy Ion Collider. So he's going to talk about his measurement of global spin alignment of vector meson at RHIC. As many of you know, Star recently published a very, very nice paper on this measurement in Nature. So our hope is that he will tell us how exactly they do that. And then later on, Luca is going to tell us something similar or something related from Alice. And then we'll have some discussion about the physics underlying the spin alignment phenomena. So Subhash, maybe you can get started.
Okay, yeah, thank you, Jingfeng. So can you hear me? And can you see my screen?
Yes, please go ahead.
Okay, thank you.
Yes.
So thanks, Jing, for this nice introduction, and thanks to the organizers of this seminar series for this invitation and giving this platform to discuss the spin alignment from RHIC. And I think the next talk will discuss on the spin alignment from LHC. So this is like a perfect forum to discuss all these recent new developments. So first, so this is a brief outline of my presentation. I will start with a brief introduction to this spin alignment or in general this spin polarization measurement. Then in the second part, I will talk about the star detector and discuss a little bit on the analysis. Then the third part, I'll discuss our measurement of spin alignment of phi and k star, especially from this Beam Energy Scan program, and then I'll summarize. So let me start with the fact that in heavy ion collisions, there can be two important initial conditions. One of the important initial condition, as we know, is this very large orbital angular momentum that can be generated in the initial stage. And this plot on the bottom shows the impact parameter dependence of such angular momentum, and one can see the magnitude of such angular momentum is really large. It's of the order of 10 to the power 4. Now, since this angular momentum is a conserved quantity, it's felt by the medium, like this quark plasma, throughout its lifetime, and this part of the angular momentum that is transferred to this quark plasma, they can polarize these quarks and gluons due to this spin orbit interaction. Now, in heavy ion collision, there can also be another important initial condition, that is the strong magnetic field that we know I mean, this also has been discussed, I think, in this forum many times. The typical magnitude of such magnetic field can be of the order of 10 to the power 18 Gauss, but the lifetime of such magnetic field is very short. And this plot here shows the lifetime of such magnetic field for various impact parameters, which depends on the conductivity of the medium and also its lifetime. Now, such a strong instantaneous magnetic field can also polarize quarks and antiquarks depending on the magnetic moments, like the coupling between the magnetic moment of the quarks and this magnetic field. So they can actually polarize quarks and antiquarks in the medium. So through this polarization measurement, what we can study essentially is the role of this external angular momentum interactions and also the magnetic field. And another important thing that we can study is how the medium responds under this under this external fields like this magnetic field or angular momentum interactions. So one of the ideal candidate to study the speed polarization is lambda hyperons. One of the reason is that this lambda decays via weak interaction. So the daughter proton of lambda is emitted preferentially in the direction of lambda spin. So it's kind of self-analyzing. So one can measure this lambda polarization from the angular distribution of the daughter proton and using this formula which is shown here, and where one need to reconstruct the first order event plane psi1, which in star we did by using the forward detectors. And this right hand side plot shows the this is kind of a compilation of all the hyperon polarization measurement, but this is first time observed in the RHIC Beam Energy Scan program in the energy between 7.7 and 62.4 GeV. And this measurement also extended to the higher energy, to Alice, and also to the lower side by Hades. So this kind of gives the first evidence of the polarization of both the species, lambda and anti-lambda. So this tells us the presence of the vorticity in the quark-gluon plasma, and based on the thermodynamics, one can extract the strength of the vorticity, and from the RHIC BS, the number that we extracted is of the order of 9 into 10 to the power 21 second inverse, and which was thought to be, and which is considered to be one of the highest vortical fluid that can be created in a laboratory. So this is all kind of well known. Now there is also, one can also access this spin dynamics of the QCD medium and also these external fields like the external rotation or the magnetic field by using the vector mesons. For example, one can use both these K star and phi mesons. So they are spin 1 particles, so they can have in a spin state 1, 0, and -1. But for these vector mesons, one cannot measure the polarization because it's a strong decay. So what one measures is known as this 0,0 component of the spin density matrix, which we call the ρ00 parameter. And this we can measure from the angular distribution of the daughter of the vector meson. And this angle is, we call this theta star. So this theta star is the angle of one of the daughter of vector meson, like has shown here, the daughter of phi meson, the K plus, and the direction. So the angle is between the daughter of the phi, like K plus, and the quantization axis, which we considered along the direction perpendicular to the reaction plane, which is correlated to the angular momentum and the magnetic field. So what essentially this ρ00 tells us is about the probability of finding this vector meson in a spin state 0. Now, I would like to point a few things about qualitative expectation of this ρ00. Like if there is no spin alignment, so like the vector meson have an equal probability to stay in all these spin states, 1, 0, and -1, then one would expect this ρ00 value to be 1/3, and the angular distribution is expected to be uniform, as shown here. Whereas if there is any deviation from the ρ00 from 1/3, whether there is smaller than 1/3 or larger than 1/3, and accordingly the shape of the distribution of the daughters are different, kind of donut shape or peanut shape, which indicates that these vector meson have a preferential spin alignment. Now, there are certain difference between the spin alignment of vector meson and the spin polarization of hyperons. I would like to point out a few. Is like one of the thing is the feed down, like for phi and k star, they are mostly produced in the primordial state. So the feed down contribution is negligible for these two vector meson species, whereas for lambda there can be substantial contribution from the feed down. Another thing is for lambda, since we are measuring the polarization, we need the detection of the angular momentum. That's something we can calculate from the first order even plane using our forward detectors. Whereas for both these spin alignment of both these species or other species also, we can utilize both the first order and the second order reaction planes. Now, with this, let me take you through briefly about the star detector and a few analysis details. So this shows a schematic diagram of the star detector. I pointed out a few of the detector components, which is used for the spin alignment analysis. So one of the major detector, the main detector in our experiment is this time projection chamber, or TPC. So recently we have an upgrade of the TPC. We have this new part which is called the inner TPC or ITPC, which extended our rapidity coverage from ±1 to ±1.5. Used for tracking of the particles, and also we use the centrality and also the even plane by using this time projection chamber. So this is like one of the major component in the spin alignment analysis. We also have other various detectors for estimation of the even plane, which is essential in getting the polarization or the quantization axis. So we have a few detectors in the forward rapidity, like we have this newly installed even plane detector, which sits around the eta 2.1 to 5.1. We also have a 0-degree calorimeter, which sits at eta larger than 6.3. These forward detectors can also help us getting the even plane, which will help us in get the quantization or the polarization axis. Now, these vector mesons like phi and k star, since these are resonance particles, we cannot detect them on an even by even basis. So we them for the decay particles, and those decay daughters are identified by utilizing the detectors like time projection chamber and the time of flight. Now, a few things about the analysis procedures. This is like a very brief outline of or the different steps that we use to calculate this rho 00. So as I said, this rho 00 we extracted from the angular distribution. So the first thing what we estimate is the yield, like we reconstruct the vector mesons in various cosine theta star pins, and then like we calculate the yield of the vector mesons in the cosine in these cosine theta star bins, and then we feed the distribution function, and from that we extract the rho 00, and then that rho 00 is then corrected for several detector effects. And in this analysis we used mostly the detector simulation framework inside star, and then these results are corrected for the even plane resolution. Now, as per the even plane, one can use two different type of even planes, like second order or first order. And in star, we use the TPC and ZDC, which sits at different rapidity, like TPC in the mid rapidity, where the ZDC is the forward rapidity. So there can be effects from the even plane decorrelation. So if one wants to compare the rho 00 from different even planes, one has to take care into account these even plane decorrelation effects. Okay, so now with this, let me now go to the results from the beam energy scan. So this presentation for mostly the measurement from the RHIC beam energy scan, and we will show the results from the energy starting from 11.5 to 200 GeV. All our measurements are done in the mid rapidity between ±1. For the reconstruction of the vector mesons, we used two techniques: the mixed event for the phi and the track rotation for the k star. And our polarization axis we consider two different types of polarization axes. One is perpendicular to the TPC, which is our second order event plane, and one is perpendicular to the ZDC, which is the first order event plane. And as a consistency check, we also measured the polarization, the spin alignment with respect to a random plane. So let me now go to the first part of the analysis, where we need first to reconstruct the invariant mass of these vector mesons. So left and right here shows the invariant mass distribution for the phi on the left and the k star on the right. They are reconstructed in their hadronic decay channels, phi in the k plus k minus and k star in k plus and pi minus. Actually, for the k star, we have included both the particle and the antiparticle, that is k star and anti-k star. So for the phi, we shown this distribution for goal 27 GeV for the PT 1.2 to 1.8 GeV, whereas for the K star, we're showing this from 54.4 GeV, where we have the highest number of events or high statistics. Now, this invariant mass, what we do, we get this invariant mass in various cosine theta star bins, and then we calculate the yield of these vector mesons in the various cosine theta star bins, which is shown in the next slide. So this slide, the left plot shows the phi meson yield from goal 27 GeV mid central 20 to 60% centrality for the moment PT between 1.2 to 1.8 GeV in 7 different cosine theta star bins, whereas on the right hand side this shows the same distribution for the K star from a different energy 54.4 in a PT between 2 to 2.5. Now, as you can see, these yields are kind of corrected for all these detector effects, and then we fit the distribution with the function as shown here, and we extract this rho 0, 0 from the fitting, and then we apply the corrections for the event plane resolution. So the next,
Subhash,
yes.
Before you go forward, can you go back? I
Yeah.
guess it's perhaps a question that is common to the series, I guess. So these are all angled in the rest frame of the decay particle.
Yes. So this
like in the phi rest frame.
Yes, exactly. Yeah. So we have, for example, we have the kaon from the phi. So then we boost the kaon to the phi rest frame, and then we calculate the theta star of the kaon and the direction of this, which is perpendicular to a reaction plane. Yeah.
Okay, that's good to know. One more question. Go back one more. So when you say that the track rotation, what does that mean exactly?
I see. So sure. So like for the phi meson, if I say it decays into K plus and K minus. So in experiment, we cannot detect the phi meson on an even by even basis. So what we measure is only this single hadrons. So one has to reconstruct the phi meson from this K plus K minus combination. Now, if you do the K plus K minus combination, you will not see the phi meson clear peak. So there will be some kind of background. So to reconstruct the background, we use the one is called the mixed event, where we take the kaons, one daughter kaon from one event and another is from another event with similar characteristics. And in track rotation, what we do, we rotate one of the track to break the correlation between the pairs. So that kind of gives us a combinatorial background, and then we subtract them from the same event. And after that, you can see this peak.
You mean you rotated the track from one event randomly with respect to another K minus from another event?
No,
like randomly.
In the same event, you can. In the same event, we rotate one of the tracks
randomly.
Yeah.
Okay, thank you.
Like 180 degrees, we can rotate.
Okay, I see. Okay, thank you.
So this track rotation just breaks the correlation between the K plus and pi minus, like the daughters of the vector meson. This is like a very kind of standard technique in our experiment to reconstruct the.
I'm sure the experiments know that, but I just want to clarify that for
sure.
Serious. Yeah, sure. Thank you. Yeah.
Okay. So let me continue. So I think, So before going to the RHIC beam energy scan, this shows the first spin alignment measurement of phi and k star that we reported back in 2008. And this analysis was using only about 23 million events that time from goal 200 GeV. And in this measurement, we did not see any large deviation of rho 00 for both phi and k star. So these results were kind of largely inconclusive and dominated by uncertainty. But in this beam energy scan, we also have many advantages. One of them is this recent, the upgrade that we have is upgrade of time of flight, which kind of enhance the signal to background ratio for all these particles. Like for phi meson, there's about factor of 10 improvement. And we also have many, improved understanding of the detector corrections like efficiency, acceptance, and event trend resolutions. Okay, so this is our new measurement of the spin alignment from the RHIC Beam Energy Scan program. This plot shows the rho 00 as a function of beam energy. These red markers are the phi mesons from momentum 1.2 to 5.4 GeV, and the K star is done within 1 to 5 GeV. And as you can see, the phi mesons are largely, mostly larger than 1/3 in all these BS region, whereas K star is kind of fluctuating around 1/3. So if one integrates these data points between 62.4 and below for the phi, one would end up the deviation of rho 00, which is 0.35, with which is, and considering the statistical and systematic uncertainties, will end up with about 7.4 sigma significance. Whereas for the K star, if we integrate, we have the results, the value of this K star rho 00 is largely consistent with this unpolarization baseline, which is 1/3. Now we also have.
Sorry, can I ask a question? Right, the 2 points at what is it, 20 and 27 or whatever? How far apart are they in terms of number of sigmas? The 2 points with the smallest error bars. The next
this
one,
one, right?
That one and the next one, yes.
This one and this one.
Yes.
Yeah, this one I don't exactly remember, but this should be of the order of 4 sigma or above this point, or maybe 5 sigma. I think this is more than 5 sigma.
How far from each other?
Oh, these 2 points you were saying,
yes.
And this
it looks also like more than 3 sigma, is it? And then the next question is that it doesn't either. There's some very weird physics, or the points seem to fluctuate. These 2 error bars are very small.
Yeah, this we do not know whether there is any kind of physics here. This could be some kind of fluctuation from the measurement. Yeah, this I do not have a clear answer. Why these points is like slightly different. This could be, yeah.
Okay.
Yeah, maybe I can also get back to this after this talk. Yeah.
Okay, yeah. Maybe you can discuss later. Yeah.
Yeah, sure. Yeah. So the next slide is I'm showing the measurement of the transverse momentum dependence of rho 00 for phi is showing on the left-hand side panel and K star on the right-hand side panel. So for the phi, the measurement is done using 2 different kinds of polarization axis. One is perpendicular to the second order event plane shown by these red markers, and one with respect to the first order event plane shown by these gray markers. So the measurements are shown for different beam energies: 11.5, 19.6, 27, 39, 62.4, and 200 GeV. We see the rho 00 using these 2 different estimations are kind of consistent. They are mostly follow the similar trend. And the large signal for the phi meson that we see is between 1 to 2.5 GeV for almost all the energies, or it is the lower energy that we measured here. For the K star is shown on the right-hand side for 11.5, 14.5, 19.6, 27, 39, 54.4, and 200 GeV. And for K star, we see it's mostly consistent with 1/3 with very large uncertainties. whereas the energy where we have the high statistics, like 54.4 GeV, we see in the mid PT region, there is a slightly enhancement, and then but at low and high PT, they are mostly kind of consistent with 1/3. We also measured this spin alignment as a function of centrality. This is shown here for phi on the top row and the K star in the bottom row. So the top row for the phi is shown again for these two different kinds of even plane, the first order and the second order even plane. And the measurements are done for 4 different energies, 27 GeV, 39 GeV, 62.4, and 200 GeV, whereas for the K star, we reported this for 39, 54.4, and 200 GeV. So what are the observations? That we see that for the phi, especially at low energies, we see in mid-central and peripheral collisions, the phi spin alignment is larger than 1/3. This is also true if we go to the highest RHIC energies. Whereas if you look into the central collisions, and especially at the highest beam energies, we see that the phi spin alignment is smaller than 1/3. Whereas for the K star, it's largely fluctuating around 1/3. But in the central collisions at 200 GeV, we see both the phi and K star gives a signal which is smaller than 1/3. So we also did a measurement of phi using a different quantization axis. Like one can have the polarization axis that is perpendicular to the reaction plane, and one can be in plane, like along the impact parameter direction. And this is shown by these blue diamond markers. We see that the magnitude of the rho 00 in plane is kind of smaller than what we measure, which is out of planes, that is perpendicular to this reaction plane. Now, so we have this recent measurement of phi and K star spin alignment from RHIC. So the next question is, how do we understand these measurements? So there are various physics mechanisms that can drive this rho 00 either larger than 1/3 or smaller than 1/3. So those are kind of listed here. So I'll kind of take you through those different contributions. So as I said in the introduction slides, that the vorticity and the magnetic field can polarize the quarks and antiquarks, and those polarized quarks and antiquarks can coalesce and produce hadrons, and that kind of contribution we call C lambda can drive the rho 00, and the expected the expectation is that that rho 00 will drive the rho 00 to smaller than 1/3, which we call negative, but the expected magnitude is 10 to the power -5. And this C lambda term is actually can be constrained also by the lambda polarization measurement. There can be theory also suggests there can be other contribution, like a term like vorticity tensor can also contribute to this vector meson spin alignment, which will drive the spin alignment to be smaller than 1/3. But again, the expected magnitude is again smaller, which is of the order of 10 to the power -4. The electric field that's also can cause a spin alignment to be larger than 1/3, which is positive, but again, the magnitude is again really small. Same for the fragmentation, which is another mechanism for hadronization, which is expected in the high PT region here, and also depending on this this mechanism, the rho 00 can be either smaller or larger than 1/3, but the magnitude is expected magnitude is 10 to the power -5. There are also these recent new developments like this local spin alignment or the contribution from the helicity, the fluctuation in this axial field, which we call this turbulent color field, can drive the spin alignment to be smaller than 1/3. But more recently, there is another mechanism that is proposed by the theory colleagues, is a vector meson strong force field, which can cause a really large spin alignment and a positive signal for the phi meson. So what is predicted is that like an electric charge in motion can generate an electromagnetic field. Similarly, these fluctuating S and S bar quarks can generate an effective phi meson field, and such phi meson field it can polarize S and S bar quarks, and those And due to this large coupling constant, this can give contribute to a very large value of the phi meson spin alignments. So this model kind of explain our measurement at RHIC, and based on this, we can extract the strength of such a vector meson force field, and which we estimated from this our data, which is turned out to be around 4.6 MPi square. Yeah. So here also a few detailed look on the centrality dependence of the ρ00. I showed here only for the phi meson for 200 GeV, and so we also have a very recent a prediction from the models, this vector meson model, and where we can see that this model predicted this ρ00, which is kind of positive across all the centralities, but what we see in our data that in the most central collisions, the ρ00 can be negative, and there are kind of calculations which indicated that this could have a contribution from local spin alignment, and this is something we see very strongly at our highest RHIC energies. This shows the transverse momentum dependence of ρ00 for the phi mesons. So these gray markers are actually the measurement that we reported in our Nature paper, and the red markers is the measurement from our recent BS2 around 19.6 GeV. So one can see that from this BS2 data, this preliminary data, we can see this deviation of this ρ00 from 1/3 is really large, and we can reach about 5 sigma significance using this single data set. And the model can also kind of expect can predict the pattern that we see in the data for the ρ00 as a function of transverse momentum. Now the next question is like we have kind of sort of explanation for the phi meson from a model. So what's the expectation for the K star? So the K star is kind of complicated because I mean primarily for the two reasons. The one reason is the quark content. I think I have a typo here. So yeah, so the K star is the constituent quarks is ds bar, whereas for phi it is ss bar. So because of that, in this vector meson force field picture, I mean, what they assumed is this the correlation between the different vector meson fields, like from D and S, they can be smaller compared to the correlation between the same field for the phi, like we have the SS bar. Another reason that we have is the lifetime. So the K star has like a factor of 10 smaller lifetime compared to phi. So K star spends more time in the medium. So recently in STAR, we also measured this K star over K ratio from the BS energies. And we also have this phi to K ratio. One can see there's a clear centrality dependence, which indicates that this K star can be affected by these in-medium interactions. But we need actually more inputs from theory to understand our K star results. Now, recently, we also reported the measurement of spin alignment in the isobar collisions, which ruthenium and zirconium species. So both these species have events of about 2 billion each. So this allows us to do the study of the spin alignment for separate species for K star and anti-K star. Whereas for the gold, we reported like a combined particle and antiparticle. What we see here, like for both ruthenium and zirconium species, I mean collisions, the red and blue, the K star and anti-K star are kind of consistent across all the centralities. And when we compare it with the gold systems, one can see that at a comparable end part, the ρ00 between the gold and the ruthenium are kind of comparable. So this brings me to my summary. So at the RHIC PS, we see for the first time a very large signal of phi meson ρ00, which is really larger than 1/3. And if we integrate within the energy 62.4 and below, we have a significance of about 7.4 sigma. For the K star meson, on the other hand, we see this is largely consistent with 1/3 across the beam energies we studied. So this surprising trend for the phi meson it cannot be explained by so-called conventional mechanism, like driven by the vorticity or electromagnetic fields. We have many new recent developments to explain this spin alignment, large spin alignment for the phi meson. So some of the models, like the vector meson strong force field, can capture the trend that we see for the phi meson. There are also other developments are ongoing, like the effects from gluon fields or plasma fields. The contribution from the local spin alignment or helicities are also important. We see the spin alignment sign is negative in the central collisions, and especially like at the highest RHIC energies. As an outlook from the experimental side, in STAR, we are working on very high precision measurements from the second phase of the Beam Energy Scan 2, which will give a very precision measurement of the rho 00 for these two species. And I have also shown one example from RHIC 19.6 GP. And we're also measuring the rho 00 of various other species. So I hope these measurements will help us understand better this spin alignment. So yeah, with this, I would like to thank you for your attention. And I'd also like to thank all the STAR collaborators, and especially the analysis team of this spin alignment. Thank you.
Thank you, Subhash. Thank you for your very nice talk, and I think you keep the time very well. So I think there are some questions here. Maybe I think it's a good idea to first just quickly visit some of these questions related to your slides from Wooly. Can you go back to slide 19 very quickly?
Okay.
I think we should wait for the question for answer, because otherwise one speaker gets more questions than the other.
Okay.
I think
so you want to wait for till the end? Okay. Yeah, that's fine. Yeah. Okay. We can take a load and we can do that later. Wooly, that's what you want, right?
But I have a question to one of the data points.
Okay, go ahead.
So if you go to slide 31.
31, yes, just a minute.
So you said that the isotope results and the gold results are compatible. That's maybe true, but you also say that the K-star polarization in gold-gold is compatible with 0, and it's clearly not compatible with 0 in the isotope run. Is that correct?
Yeah, that's correct. Like if you look at the peripheral bins, the is not
so okay, but then in your summary you would have to qualify that the K0, the K-star polarization in gold is compatible with 0 with large errors, but in the isotope run you will find a very significant signal. That's also quite a few sigma if you take zirconium and ruthenium, isn't it?
Yeah, that's correct. Yeah.
Okay, so that somehow complicates the picture, doesn't it? Anyway,
yeah,
so that's correct. So you find also a K-star polarization. Okay.
And at 200 dB. So I agree that it's confusing in some sense. Yeah.
Yeah, but the important point is not only the phi as a positive, but also the K-star has a clearly significant positive correlation, even if you average over all 3 runs.
Yes, that's
it looks
correct.
like. Okay, good. Thanks.
Okay, I guess maybe it makes sense to move forward next talk, and then we come back and discuss all the together. Okay, thank you very much for the nice talk by Subhash, and then let's move on to the next speaker. So we'll have our next talk from Luca Micheletti. Sorry if I didn't pronounce your name correctly. But Luca will give us a very nice talk, I guess, about the vector metons polarization from both the PPE to lead collision and the RHIC energy. So please go ahead.
Yeah, so thanks a lot for the presentation. Can you hear me well?
Yes.
Yes.
Okay, thanks. So as mentioned before, I would in my talk I will discuss on vector meson polarization from small to large systems at the LHC, providing a general overview. So for what concern the introduction, many concepts have been already discussed in the previous talk, so I will move quick through them. So the main topic of the presentation is vector mesons. So we can express the total angular momentum of vector meson as a linear combination of 3 different eigenstates, as shown in this formula here. And the polarization and the spin state is basically expressed also as a function of the 3 coefficients that are b plus 1, minus 1, and 0. For sure, we cannot directly access this quantity, but we can extract it thanks to the angular distribution of the decay products that follows this functional shape here that can be basically derived from first principle and in the paper that is reported here. And as you can see, this functional shape depends on the polar and azimuthal angle theta and phi that are measured as the angle between the quantization axis, in the sketch is the z-axis, and one of the 2 daughter particles. So for a project psi, for example, is the positive lepton. This quantity depends also on the polarization parameters that are lambda theta, lambda phi, and the lambda theta phi. And if all the parameters are null, we can see that the distribution is basically isotropic. So we have, as a function of cos theta, the flat line, the flat gray dashed line. But if we have, for example, lambda theta equal to +1, we have the red curve that corresponds to transverse polarization, while if lambda theta equal to -1 corresponds to the blue curve that is typically called in literature as longitudinal polarization. In the previous talk, you have seen everything, all the measurement for polarization as a function of the spin density matrix element ρ00 that is connected to lambda theta. In particular, just to provide a simple connection, if lambda theta equal to 0 correspond to ρ00 equal to 1/3, so there is basically no spin alignment. And one extra caveat is that the connection among lambda theta, lambda phi, and the spin density matrix element depends on the spin state of the system of daughter particles. So this can change if we consider a dilepton system of or a dihadron system, but this will be shown in the following slides. Another that is crucial is the definition of the reference system. So basically the definition of the quantization axis with respect to which we measure the angular variables. Because typically we can use the helicity, that is the most intuitive, where the axis is the direction of the vector meson in the laboratory rest frame. We have also the Collins-Soper, that is the bisector of the angle formed by the 2 colliding beams as seen by the vector meson rest frame. And finally, we have also the event plane base frame, as already presented in the previous talk, where basically we use the axis orthogonal to the event plane of the collision. And this it can be interesting because this gives us the possibility to access information related to the strong angular momentum that can be produced in heavy ion collisions or the magnetic field. Then, so we can move to the first set of results starting from small collision systems. In proton-proton collision, the main purpose to study polarization is to investigate the quarkonium production in particular, because this is the polarization is sensitive to the process. And before the LAC, there were several theoretical predictions that works rather well for the cross section, but they are obtaining very different results for what concern the lambda theta parameter, for example. And here I'm just showing a plot for the GPSI measurement from CDF compared with an RQCD leading order in yellow, and in the light blue we have the color singlet model. And as you can see, you get exactly the opposite. So this makes clear why measuring polarization is interesting, because we have a very strong observable to discriminate among different production mechanisms. But at the same time, this gives us something that is ambiguous in the interpretation, because the measurements stay basically between the predictions. So the expectation before LHC is that with the new measurement with higher precision, we could basically shed light on this ambiguity. And the result obtained by both ELIS and LHCb, for example, are compatible with a scenario of zero polarization. You see here the lambda theta, lambda phi parameters in the two reference frame, Collins-Soper and helicity, as a function of the transverse momentum. And you see that the measurements are in agreement with the various energies and the different experiments. And there is no hint of a strong polarization as expected, for example, by theoretical predictions. Since models were saying that at very high PT we could expect to see large polarization, CMS extended the PT region up to 70 GeV for JPSI, for example, hoping to find this deviation, but this was not the case, and all measurements are again compatible with zero. So this clearly was a problem from the theory point of view, because no model available at the time was able to describe properly the polarization of JPSI in particular. So there was a big effort by different theory groups. I would like to mention two of them that are in particular working with the NRQC next to leading order in the framework of the color glass condensate, which is the first one on top panels in light blue, and the improved color evaporation model, which is another model used to describe quarkonium production and polarization. And as you can see now, we don't see the large deviation with respect to zero as for the first predictions. And we are much closer to our measurement. So this is for sure something important and give us the feeling of all the work done to understand better this observation. Then, for sure, the effort from the experiment is not only for JPSI, but also for the excited states. We have in run 2 of LHC, we have a big sample for Psi2S and Psi2S in particular, but also Chi-C, that allow us to perform polarization measurements. And for the Psi2S, the measurement is compatible with zero, as shown in this slide. But for the Chi-C, interestingly, CMS found this deviation for the relative polarization among Chi-C1 and Chi-C2. Because as you see in the plot on the left, basically they extract the polarization, so the lambda theta parameter, for the Chi-C2 as a function of different constraint for the Chi-C1. So in one case it's unpolarized, in the other case is constrained to be the NRQCD, the value extracted by NRQCD. And in both the cases, you get that the relative polarization is big among the two states. Unfortunately, the statistic and also the difficulty of the analysis, because the Chi-C decays to a JPSI that is rather easy to detect, but in addition, there is also a soft photon. So this makes the reconstruction much more tricky, and so it's harder to get a very precise measurement, but this is already a very good point. Moreover, with this measurement, some theoreticians were already able to get some constraint on the JPSI polarization, but coming from the decay of Chi-C1 and Chi-C2. That shows how important it is to extract the polarization for excited states. In particular, taking into account that 30% of the prompt JPSI comes from Chi-C and 10% from Psi2S. Then there is also huge work to extract polarization from Bottomonia. We have measurement from ELIS, CMS, and LHCb. In the panel on the right, you see the lambda parameters extracted by Ellis and the LCB at forward rapidity. And you see that the deviation with respect to 0 is small, with a mild dependence, which is predicted by models, while CMS focused on the excited state.
Somehow we lost your sound, Luca.
Sorry, can you hear me?
Now you're back, but you were off for a moment.
Okay. Okay, no, my headphone just disconnect for for a while.
Okay.
Sorry.
Now it's okay. Yeah.
Now it's okay. I can hear you back.
Yeah.
Okay. So just to continue, so CMS measured also the excited states with good precision. And what they found is that within the uncertainties, they don't see a strong polarization. They are basically all compatible with 0, which is interesting because contradict a bit the measurement, one of the first measurement obtained for the combination of 2s and 3s, where a strong polarization has been extracted. Then I would like to conclude with one of the most recent measurement performed by Ellis, which is the ρ00 parameter extracted for the star for prompt and non-prompt component. It is indeed the first measurement of this observable for open charm at 13 TeV. And what has been observed is the polarization is compatible, the ρ00 parameter is compatible with 1/3, so there is no polarization. While for the non-prompt, we see a significant deviation that basically can be interpreted as an effect of the helicity conservation in the decay of B hadron to a vector meson. Apart from the measurement itself, the result is very important because it provides a baseline for the study of polarization in a lead-lead collision that is for sure foreseen in future and new data taking. Okay, so this concludes the part of a small collision system, and we can large collision system. So for sure, measuring polarization here means to investigate different time scales and different kind of mechanisms that were already summarized in the previous talk. I just provide a very quick overview of them. So first of all, we have the magnetic field that is short-living and is characterized by a huge intensity. And it's not from theory prediction, we don't see a strong dependence on the impact parameter. For example, I would like to mention this paper here from Karziev et al., where you can see, for example, at 200 GeV, the dependence of the magnetic field as a function of the time. So you see that it increases very quickly in basically 1 Fermi over C. At the same time, we have the effect of the angular momentum that affect the whole system evolution and exhibit a strong dependence on the impact parameter, as shown, for example, in this paper from Beccatini et al. So these are two important mechanisms, and there are some quantitative predictions. In particular, in this paper, they mention the effect on ρ00 of the angular momentum and the magnetic field. And in particular, for the magnetic field, we would expect a different sign according to the charge of the study. While for the angular momentum, the effect is always negative deviation with respect to 1/3. And it is equal for all the vectors meson. But this is not the full story, because, for example, looking at quarkonia, we have other mechanisms at work. For example, suppression that is well known, and it's basically the dissociation of the state inside the quark gluon plasma due to a color screening effect that has been widely observed at RHIC and at the LHC. But also the regeneration, which means that there is a recombination of the uncorrelated CC bar pair inside the medium when once the multiplicity of them is very high. And this, for example, is very well visible when we look at the comparison between Alice and Phoenix, for example, where we have the nuclear modification factor as a function of PT. And we see this big deviation among the two results that is typically interpreted as an effect of the regeneration that is more significant at LHC, so a larger number of CC bar pair is produced, and this impact more at low. So after this brief introduction, I want to move to the measurements. So the first one is the measurement of the ρ00 parameter for K star and phi vector mesons performed by the Alice collaboration. The result here is obtained in the event plane reference frame, in the production plane with a random event plane. And what we have seen is that in event plane, there is a significant deviation, in particular for the K star at low PT with respect to 1/3. There is also a deviation for phi, but is less significant. Then, in order to validate a bit the measurement, the procedure is applied to the K0 short, that is a spin zero particle, so should not be influenced by, could not be polarized, and the result shows that that are in the cross in pink, that the measurement is compatible with 1/3. Finally, the measurement is repeated, but in proton-proton collisions, where again we could not expect any polarization from, for example, angular momentum. And we see that also in this case, the points are compatible with 1/3. Then we can do the same measurement as a function of the collision centrality for both K star and phi. And what has been observed is that the maximum deviation is for low PT and semi-central collisions. And this is valid both for phi and K star. And this polarization basically disappears once we look at very high PT. And this is basically consistent with the quark recombination at the phase boundary. That is the scenario predicted by the paper I'm reporting here. Then moving to our probes, we have the measurement of GIPSI polarization in so in this case, we extract the three polarization parameters, lambda theta, lambda phi, lambda theta phi, and in this case, we see that that are the red points. The red points exhibit a maximum deviation of 2 sigma at low PT for the lowest PT beam, and the measurement is compatible with the green points that are the Alice results in a proton-proton collision. So these results seems to suggest that there is no significant modification from proton-proton to lead-lead for GIPSI. But at the same time, if you look at the very precise measurement performed by LHCb in a similar PDT window, in helicity we observe this deviation that is about, the difference is about 3 sigma. So these could be induced by different effects that are at work and that cannot be, appreciated with the Alice measurements, since the statistical and systematic uncertainties are much larger. So for sure, in order to shed light on this difference, the best thing is to repeat the measurement in proton-proton collision with the highest data sample available with Alice and see if we see this deviation. So in order to have a one-by-one comparison. We have also the measurement of the epsilon-1s polarization. Unfortunately, in this case, the statistic is very low, so it's not possible to perform a differential measurement. But this already tells us that we can do it. So with, in particular, in run 3, or for example, CMS that has a big epsilon data sample could perform already the measurement and extract the polarization for the epsilon. That could be already a very interesting result. Moving in the direction of theory, for the moment, there is no a full comprehensive description of polarization of quarkonia in heavy ion collisions. We start to have some theoretical works in the framework of the improved Kobler evaporation model. They tried to inject the cold nuclear matter effect and evaluate how much they are supposed to impact on the polarization. So in the plot on the left side, you see the lambda parameters for PP and lead-lead collisions. Just taking into account that in lead-lead we have only gibbside direct production and only cold nuclear matter effects. So for the moment, there is no QGP-like effect. What we see is that the difference is very small. So at the level of the uncertainty we have now, we cannot appreciate this kind of effect. But this is already a very good starting point in order to then add the hot nuclear matter effects that could be much more interesting for our case. Then I would like to conclude this part showing one of the last results, that is the extraction of the lambda parameter in the event plane reference frame, again taking the orthogonal to the event plane of the collision for the GIBSI. And this measurement is done first of all as a function of the collision centrality. And even if within the uncertainty it's we cannot say anything about the trend we observe, we can see that the maximum deviation is again for semi-central collision in a PT region that goes from 2 to 6 GV/C of the GIBSI. One more thing to remind is that we are studying GIBSI decaying to mu plus mu minus. So this means that the connection among GIBSI and ρ00 is this one, which means that a positive deviation with respect to 0 of lambda theta correspond to a negative deviation with respect to 1/3 for ρ00, and vice versa. So a negative deviation for lambda theta corresponds to a positive deviation for ρ00. We can inspect also the PT dependence for different centrality classes, central event 0 to 20% in red, and semi-central 30 to 50% in blue. And what we see is that the maximum deviation corresponds to the lowest PT bin for semi-central collision. So this tells us that qualitatively we are in agreement with what has been observed by Ellis for K star and phi, where the maximum deviation is again for low PT semi-central collision. But since we don't have for the moment a comprehensive theory, it's not possible to say if this effect is due mainly to the vorticity or to the magnetic field. As already very detailed explained in the previous talk, there are predictions for the phi meson. So it would be great to have something similar also to GIBSI, because this would really help in the interpretation of our measurement. So this brings me to the summary. So in the summary, I just want to present the status of all the polarization measurement for vector mesons at the LHC. So starting with the light vector mesons, just one more detail. I decided to present the result with the ρ00 for simplicity, because the fact of passing to lambda theta and the ρ00 it makes things a bit complicated. So I just convert everything in order to make the comparison easier. So for what concerns K star and phi, we have basically the measurement in proton-proton, where we see that the effect we see that there is no polarization, so ρ00 compatible to 1/3, while in lead-lead we see a negative deviation, and this is compatible to the scenario of polarization via spin-orbit coupling of the quark inside the medium, and then the polarization is transferred to the final state. For what concerns the star, we have one measurement in PP, where for prompt there is no deviation with respect to 1/3. This measurement is interesting because it provides basically an interplay between quarkonia and light flavors. And it would be even more interesting if we decided to look, if we can look also at the different charges, because from the model I have shown you before that describe the impact on rho 00 due to the magnetic field and vorticity, we have seen that for magnetic field, the deviation could be positive or negative according to the sign of the particle, so according to the charge. So we would expect that for particle with a similar mass but different charge, this effect is the opposite. So measuring this, we could really put some constraint on the different effects of vorticity and magnetic field. For GPSI, we have an effect that looks qualitatively, at least, compatible with what has been observed for light vector mesons. But the GPSI is a bit more complex because it is the heavy quarks are produced in the very first phases of the collision. So in principle, they are more sensitive to the magnetic field. But moreover, we have also the effect of suppression and regeneration that could impact on the final polarization. So we need, in this case, a very comprehensive theoretical picture to very understand what is happening. For the excited states, for the moment, we have only the measurement in proton-proton with the interesting case of the KC that exhibit a strong deviation with respect to rho 00, with respect to 1/3. For the lead-lead, for the moment, we don't have anything, again, because the KC in particular is very tricky and complex. So for the moment, it is not possible to do it. Hopefully, in new data taking, we would have more possibilities. Finally, there is the case of botomonia, where in a PP, we don't see a strong deviation with respect to 1/3. Also, for the moment, for sure, even if the statistic is still very limited, but the upsilon is indeed a very interesting resonance, in particular the upsilon 1s, because we know from V2 measurement that the regeneration is compatible, that we have no flow, we have no elliptic flow. So this is compatible with a scenario of no regeneration. At the same time, the big quarks are produced even earlier than the CC bar quarks. So in principle, they are much more sensitive to the magnetic field. So in principle, upsilon is a very interesting case. Moreover, due to the signal to background ratio, it is already feasible even with a low statistic. So this could be something, I think, in ALICE in run 3, but also, for example, CMS with the huge data sample they have already in run 2. Could perform, and it could be very nice measurement. So that's it from my side, and thanks a lot for the attention.
Thank you, Luca. Thank you for that talk. I guess we should maybe get into the question and answer session with also for some free discussion. You know, to make it simple, let's start with any question for Luca before we move back to the question for previous talk. Any question for Luca for talk? So I maybe I'll start just by asking some questions. So what do you think of this rho 00 less than 1/3? Obviously, that's, I mean, in my personal opinion, this is somewhat in tension with what star has been seen. So what's your take on this?
Yeah, so I mean, this is for the moment a bit complex to say. I mean, we are comparing different energies. I mean, star is up to 200 GeV, while ALICE is 5 or 2 TeV. So there is one order of magnitude of difference. The current interpretation of this is the spin orbit coupling, as mentioned before. So I remember that in the figure shown in the previous talk, the points of ALICE are also shown when comparing rho 00 for light vector mesons. But in that case, it's harder to say because the statistical uncertainties are very big. So I mean, I have no answer for the moment. I understand perfectly that there is this sort of tension, but for the moment, I guess it's not yet fully understood.
Okay, thank you. I think Bernd had maybe question and comment. Please go ahead.
Yeah, thank you. I have a question actually to both speakers. The phi meson also shows up in the dilepton spectrum. And I think both Star and Alice can measure dileptons in this invariant mass range. Can you deduce the ρ00 from those measurements?
Yeah, this can be done. This can be done, but for the moment, we don't have the measurement in the dilepton of the polarization in the dilepton channel for the phi. But I think that we have the statistic and we can do it.
Could the Star speaker also answer that question?
Yeah, I just unmuted myself. Yeah, so but yeah, that's right. So in Star also we can, take a look at phi in the dilepton, and actually some analysis group already started looking into this. So we hope by this time, this upcoming quark matter, we should have some result of phi meson in dilepton channel. Yeah, so those analyses are like in the very preliminary stage, but yeah, I mean, we are kind of taking a look at this phi ρ00 in dilepton channel as well.
Okay, did that answer your question, Bernd?
Yes, I understand. We have to see what the results are, whether they confirm the measurements in the K-meson channel.
Okay, so we'll have to wait till September to see that. Okay, next question. I think Shini, you want to make some comment or question?
Yeah, I have some question about Jinfeng's question. So you mentioned that the spin alignment for GIPSI is very different from the spin alignment of phi meson. So I think this may be two reasons. First, the GIPSI meson is measured in the very forward relativity region. You can see from this finger, this Y is from 2.5 to 4, but the phi meson spin alignment is measured in the mid rapidity region. So it is one. And the second possible reason is that the GIPSI is produced in the very beginning of the collision. So Luca also showed this. So the life of CC bar is approximately 0.1 from over C. It's so the GIPSI spin alignment may be related to the fields in the very early stage.
Wait. At LHC, it's at least conceivable that most GIPSIs are made at the phase boundary by regeneration. Remember.
At low PT, yeah.
And particularly at low PT, where.
No.
So that is another complication.
Yeah.
Okay.
And okay, sorry.
Yeah. So my point is that the phi meson measures the fields in some later states, while GIPSI measures the fields in the very early stage. So
no,
that's
not if it's coming by regeneration.
Yeah, yes, I know, but yeah, but the regeneration process mainly contributed to the very low PT region for the GIPSI. I think for PT larger than 5 GeV, the regeneration process contributes less.
Yes, but the yield is dominated here by the
low
2
PT.
to 3 to 4.
Yeah. So this needs a more detailed simulation. Thank you. Yes.
Yeah. For what you said, just the comment for what you said about the rapidity, this is true, because we are basically comparing two different rapidity regions. Unfortunately, in run 2, we cannot do this kind of differential measurement at mid rapidity in the dielectron channel. Basically, it's a reason of due to the statistic. But now in run 3, we will have the possibility to have basically triggered events also at mid rapidity. So this increase a lot the statistics. So we will have the possibility to measure basically the same as the phi and the k star, so in the same rapidity region. This would help a lot in the comparison.
Yes, thank you.
Okay, I think there's a relevant question also related to phi meson from Ian. So he made a comment about the phi lifetime. So you want to ask your question here?
Yes, I'm just yes, I'm asking question maybe also for the audience. Is I heard people always are saying the phi meson, the mean free path is very long. But yeah, but I just noticed there's some very early work by Fokker and his collaborators claiming the mean free path can be as of phi can be as small as like 2.5 fermions. So my question maybe is just do we really know what is the state of art of the understanding of phi meson's mean free path? And that's my first question. And my second question, maybe even more naive, is how do we know if the rho 0, for phi in vacuum is 1/3? Do we really know that from? Do we? Yeah, that's my two questions.
Just to clarify, what do you mean by phi meson is a single phi meson? It's perfect.
Yes, whether there's a D-wave component of phi meson. My understanding is if the wave function of phi has D-wave components, then the rho 0 does not need to be 1/3.
Okay, so I don't know, Luca and our first speaker, Subhash, you want to make comment on those? Or anybody from the audience?
Yes, I think I can answer the second question for Yin. Because phi meson's CP is 1-, so it cannot be a D wave. Okay, that's my answer. It cannot be.
Right. Well, you know, phi meson, let's think it's a vector meson with usually we think of phi meson to be you know, S wave with the spin
Yeah.
1. So
Yes.
yeah. Okay, so I think you're right. Unless we have compelling evidence from hadron physics to say that phi has some D wave component. Otherwise, I guess it had to be S wave, I guess. You have any further comment on this?
No, I'm just asking. Yeah.
Okay.
Thank you.
Jürgen, you have a comment or question?
Yeah. So if we are now in the overall discussion in this whole, I mean, first of all, thank you for the both speakers for giving really a very nice overview over the many different polarization measurements. Now, if we go to heavy ions, then there are at least two big puzzles which may or may not be connected. One is if we only look for star data, because it seems, at least with current models, the polarization of the vector mesons, the phi, and it looks now also the k star, at least if I take the isotope run, is numerically not at all connected to the reasonably well understood and interpreted lambda polarization. So it looks like there are two very different mechanisms, which is surprising, but not, of course, impossible. And the second puzzle is then that the polarization dies away with square root of s, as one would expect. And we also don't see anything for the lambda at LHC, but then it changes sign for the phi and the k star. So all of this is really completely counterintuitive. We have two polarizations at low energies meaning RHIC, which seem to be from two completely different mechanisms, because numerically they are way too different. And then they change, one of them disappears, the one for the lambda, and the other one changes sign for both particles, for both phi and k star. So that really is maybe either a very rich field with many different physics, or we somehow haven't really quite understood it, or it could be experimental at both energies. I don't know, but it's a rather unclear situation how to interpret that. So there's some input from theory would really be very much welcome.
Yeah, Jürgen, I think I would agree with you that the physics of the lambda polarization and the phi spin alignment appear to be very, very different. That's my personal impression as well. So let's first ask two speakers to respond. You have any response on this question?
But then even, and that's even worse, then even the phi k star at low energy RHIC seems to be not connected to the phi k star at the LHC, because whatever the mechanism is which we currently seem to prefer, namely the phi field, that cannot switch sign.
Well, maybe there is a hadron versus parton or even plasma difference when you shift the energy substantially. Maybe Bernd will make comment later, but for now let's first ask perhaps our speaker to respond first.
Yeah, I mean,
respond to the comment that difference.
I have nothing.
Between,
I have nothing major to main add on top of what Jürgen just said. I mean, the current understanding is still kind of incomplete. We need like more inputs to understand this tension between the sign of the spin alignment between RHIC and LHC. Yeah, but the energies are very different, and the medium, the in-medium interactions can be different. There can be other physics that's playing at these two different energies. Yeah, I think we need more input from theory also to understand this data.
Yeah, lambda appear to be very reasonable. I mean, at least there's a reasonably convergence on what that may mean from lambda polarization, global lambda polarization. But for spin alignment, I think there's tension between phi and k, and there's tension between the phi at low energy and high energy. So I guess these are two important questions that we want to understand. Okay, so I'm going to ask Bernd to make comment, and then maybe Shini can make also comment, because these are, I guess, two of the possible contributors to that spin alignment. So Bernd, please go ahead.
Yeah, thank you. So the way that I think about this, Jürgen and everybody else, of course, is as follows. The polarization is an axial vector quantity, and because the strong interactions do not violate parity symmetry, that means that they can only be related to the very specific axial vectors that exist in the collision, which are imposed on the system externally. And there are really only two. One is the magnetic field, and the other one is the angular momentum. And so the mechanisms and the underlying origins of that non-zero value are extremely limited. If you don't want to postulate that they could possibly be generated by weak interaction, which seems not reasonable. The rho 0, component of vector mesons does not show the same symmetry constraints. And that means that there can be many different reasons to produce a non-1/3 rho 0, 0. And we've seen that in theoretical explanations. Now, whenever you have a quantity that is possible to generate by many different mechanisms, the likelihood is that all of them contribute to some extent, and which one dominates at a certain energy in a certain system can vary quite a bit. So I think what we see with the vector meson alignment is due to the fact that this is a probe that is very unspecific to the particular mechanism that generates, which means that theory has a hard time making a definite prediction. You could probably always come up with some theoretical mechanism that produces what the experiment measures, but that's a post-facto explanation, not the prediction. So that's a fundamental conclusion. The energy dependence, the beam energy dependence, I think it's very clear that at different energies, different mechanisms could dominate. So as an example, I like the alignment generated by plasma fields. If that's an important contribution, and our calculations indicate that it could be, then you would expect it to dominate at the highest energies where plasma is the dominant mechanism to produce the quark fluid plasma. And so that would predict the rho 0, 0 less than 1/3, and that's indeed what LHC sees. At lower energies, you expect that hadronic effects in the star range, especially if you go down in energy in the beam energy scan, that hadronic effects become much more important. And that the plasma is more or less a minor contribution. And hadronic effects, as we understand now, can indeed produce a positive rho 0, 0 that is one that's bigger than 1/3. But it doesn't specifically say this is the mechanism. I think fundamentally there could be a dozen different mechanisms that can all contribute. And quite frankly, I'm not sure how one can possibly, how one can have a good way of sorting out, except for some kind of very little constraint fit to the data, which one at which energy or which system dominates. So that's my view. Maybe I'm too pessimistic here in terms of the interpretation, but I don't see how this observable can be very discriminative of any particular production mechanism.
And may I just ask, because many QCD, many of your possible contributions are via the production mechanism, via QCD in the initial state of production. Now, they all are not compatible with the fact that in PP we don't find any polarization. So that, I think, excludes already quite a number of your big universe. If we only find it in heavy ions, and it's aligned with the polarization axis you mentioned before. It is aligned with the event plane, less with the production plane, more with the event plane. So that somehow reduces your universe of possible explanation quite a bit, doesn't it? What is left?
Sure. I mean, yes. But I mean, any of those that have been discussed have that property, right? So I'm not so sure that is sufficient. But I mean, I'm not discouraged theorists from trying. And certainly better measurements and improved measurements will help. And at the moment, as you point out, there are some real questions about the star measurements, right? Whether the errors have been underestimated.
Yeah, I kind of, when I first saw this spin alignment measurement, I thought it's so big, right? It's such a big signal that it's very, very hard to explain. Of course, now there's this idea about this strong force field. I think maybe Shini, since you raised your hand, you want to make some comment on this? Kind of responding.
I agree with the point. So for the spin alignment, it's much more complicated. We learned from the recombination model that the spin alignment measures the anisotropy in meson's resonant field. That means if the spin alignment deviates from 1/3, that means the symmetry is broken in the measurement direction and perpendicular to the measurement direction. The symmetry is broken. And this symmetry breaking can be induced by any kinds of field, such as the magnetic field, vorticity field, strong the hadronic field, or the ground field, any kinds. But for the lambda's polarization, it's much more simple. The lambda's polarization induced by the magnetic field or vorticity. It's much more simple. But the spin alignment has many different kinds of reasons, and we argued that the phi meson's spin alignment maybe mostly induced by the strong force field, but that does not mean other possible other fields does not contribute. For example, maybe in some region, maybe in some considered kinetic region, the vorticity field also contribute, and the contribution from vorticity is larger than the strong force field. So this I mean yeah. Okay, so I mean the spin alignment is more complicated and may contain many different kinds of sources, and more studies, more discussions.
Yeah, I don't know. I'm not sure what you exactly mean, but you know, vorticity field is very strongly constrained by, for example, lambda polarization measurement. So it's not going to be big enough to explain the spin alignment. It's not like not enough. It's like a order of magnitude smaller.
Yeah, but the lambda measures the average value of the vorticity, while the spin alignment is related to the fluctuation.
I understand. We checked that. So spin alignment pick up the omega over t square effect. And of course, you know, you have ion collision, you have a positive omega and negative omega. You square them and add them together over the fireball. It's still, you know, like order of magnitude smaller than what star matter has no energy. So we quantitatively check that. So it's not going to work with the vorticity. I think, at least that's my opinion, that it's not going to work with the vorticity. Jürgen, you want to make further comments?
Yes, I want. So I hear now two theoreticians waving their hands, saying this looks very difficult. But I'm not yet ready to give up for the simple reason it is a heavy ion effect. We have looked. It's not a QCD effect of some weird kind. It's a heavy ion effect. It's only visible in heavy ion collisions. It doesn't. So potentially it's interesting. Now, the first thing I think which one should do is eliminate some of the possibilities by making predictions and seeing whether we can test them. And one thing we can possibly test is the charge dependence. This with the charmed, with the D star and the D star plus, that would be very nice, because then we can immediately either exclude or confirm the magnetic field. Maybe, I'm not sure whether in principle one could do also with a K star plus, which of course difficult because then you have to do it with a pi 0. But that seems to be a very important measurement if that can be done, because that would clearly rule out a large amount of possible explanation if we can show it's not depending on the charge. Or vice versa, if we see it's depending on the charge, then we know how to measure the magnetic field. So that clearly will again reduce the possible phase space of explanations. The second, I guess, what we should do is both from the ALI side and the star side, sure that the questions about the data are addressed by star, for example, by looking how consistent or inconsistent the result is in the isotope run versus gold for the K star. It's very unlikely, unless the physics is very weird, that we have no polarization in gold and a very strong signal in the isotope run. So maybe there's something which can be done on the data to nail that down. And likewise, we probably with new data should get the significance higher in the K star and phi results at LHC. So at least from the experimental side, the data is clear. Then the question to the theorist is, okay, if there are many different sources, are there any other ways one can experimentally try to address them? I mean, I mentioned one already, which is the charge dependence, which is an obvious one. Are there any other measurements which we could do via the PD dependence, rapidity dependence on the decay channel? It was mentioned to look for the lepton in the phi versus K star. Different methods. I mean, anything which could help us to address it, I think would be very welcome, because potentially, unless makes this complicated pattern, there may be something interesting which, by just saying it's too difficult, we may not get. The fact that also the shape size shows something clearly is also another indication that this is potentially quite interesting. So my pleas, let's try to get some more measurements done, which we can make sure that we try to reduce the errors and make the data more consistent amongst themselves. For example, isotope versus gold star and the phi at LHC. But also from the theory side, give us some hints what we could do in order to at least go one step further.
Yeah, I think they are very nice suggestions. We have one question from okay. Well, okay, so we have a few questions from the chat. Let's go back to the slide of the first talk. So these are questions from Wooly. So on slide 19.
Yeah, this has already been addressed in the discussion so far, so I don't think we can go back to that. I was just trying to figure out what I should think of the fact that the deviation of the signal for the phi from 0 is as large as the deviation from neighboring energy points. That suggests to me that there may be missing components in the errors, and the error bars may be too small. But that's just an observation that Jürgen already made.
Okay, so let's then go to 22. Yes, so here's the question. How do you understand different phi meson spin alignment values?
Yeah, so how do you interpret that?
Mm-hmm. Yeah, I can have a comment. So our understanding about this is the difference between the outer plane and the in plane are mainly driven by the elliptic flow V2. So you can see this is in centrality region 20 to 60. So the V2 is non-zero, so this breaks the symmetry in the in-plane and out-plane directions. And in the other page, maybe Subhash, you can show the centrality dependence of 0, 0. Not this one. Yeah. Okay. So you can see the centrality dependence 0, 0, 0 is larger at the mid centrality region. So in this region, V2 is larger than the mid rapidity region, mid centrality region. So
you make the comment that it's correlated with elliptic flow.
Yeah. Yes.
Don't see how elliptic flow explains it.
So yeah, so I'm also curious about it. So my understanding, it may be wrong, but my understanding that you're using the strong force field fluctuation to
Yes.
explain the spin alignment.
Yes.
And you're assuming, of course, in a case where the elliptic flow is non-zero, you're assuming there are different fluctuations of the strong force field in plane and out plane.
No, we assume the fluctuations in these two directions are same. But the motion of the particle breaks this symmetry. Yeah, so if you observe in the particle's rest frame, the symmetry between these two directions are broken.
But that's well, okay, fine. But remember that the fireball is a fluid. So
yes.
You're saying that are you saying that there's a universal, homogeneous strong force field fluctuation in the lab frame? But that's
yes,
something that's not reasonable.
Yes, I agree. This is the simplest assumption, but at present it's the only one you can use. Yeah, because we cannot simulate the fluctuation in the hydrocode. So we have to put a homogeneous background.
Go ahead.
Thank you, Jimbo. So I joined late, so I only heard the second part of the discussion. I heard that people are talking about tension between data points between RHIC and LHC, saying that RHIC C rho 00 greater than 1/3 and LHC C less than 1/3. Right, this plot. But as if you look at this plot, well, the right two most data points are from Alice. As I see, the difference between the Alice data point, say the Alice, I don't know, the lower point is 4, 5, okay, star. Either of them are no more than 2 sigma away from start data points. So
that's not the latest data. That's very old. That's the first one with big error bars. So
that's the published data.
But there is preliminary data with, I think it's published by or shown in conferences at 5 TV, where the error bars are much reduced.
So
now it's clear. Now it's clear that the K star is about 3 sigma below 1/3, and the phi, I don't know how many sigma it is, less than 3, but
from the same kinematic region.
Yes. Maybe Luca can give the numbers.
So is that published?
Yeah, so for what concern the K star, the maximum deviation is 3.2 sigma in both the production plane and event plane. I think this has been obtained with the 2.76 that is for sure published. I don't know if the 5.02 TV is just a preliminary, so it's not yet out as a paper. I have to check. I'm not fully sure.
Okay. So there's another publication coming from the K-star, or because I think we checked the latest publication. That's the number we got it from.
I mean, that certainly will be published. So I'm just looking. I see where it is, at which state it is.
Okay.
Okay, this is something we can follow up. Thank you.
Dylan, you have some comment, question? Go ahead.
Yes. So I have just a kind of supplementary comments is based on this comments by Jürgens about this. Many possible QCD explanations are excluded because this absence of the spin alignments in PP. So there is also the supplementary comments is for Brent's answer. It's like in our Glassman models, the differences in heavy ions and PP is that for this spin correlations is induced by color fields. Now we have the intrinsic anisotropics of these correlations in heavy ions, where you have the stronger longitudinal scalar fields. But this anisotropics is not, its absence is in the PP conditions. And also, it's very important that if you consider the coalescence model to generate these spin alignments, the anisotropics for the spin correlation is necessary. So even you could have some isotropic spin correlation, it doesn't give you the spin alignment. So that's also the reason why, yeah, Shindy also need this kind of B2 or momentum anisotropies to generate the spin alignments with the kind of isotropics is vector meson fields fluctuations. So that's just my comment. Okay, thank you.
Thank you, Dylan. So, Shini, you have any response?
Yeah, I think I agree with Dylan. Yeah, okay. Okay, that's all.
So, any other question, comment for both speakers? Well, if no more, I guess my takeaway would be like, we still have a lot of work to do in both experimental measurements and theoretical interpretation. I guess, I mean, to me, I mean, I'm hoping that I can learn something from this today's discussion and seminars, and I feel like, well, in my personal opinion, like we have more homework to do, both for experimentalists and theorists. Let's maybe in a few months at Quark Matter, we'll see more information coming from both Star and the Alice, and I hope that you know, that we're going to be continually working on this, and hopefully find more information and understanding. You know, what is going on with the spin alignment, because it looked like to me, and like this the global spin polarization and even the local spin polarization are reasonably understandable, where the spin alignment measurements are very puzzling. So I guess that's good. In some sense, that's a good thing, because we have more questions to investigate, and hopefully, you know, in the future we can have more answers than questions, and that'll be good. So with that, I will hand it back to Ian. So you have any further comments, or should we conclude?
I think we can conclude. Yeah, thank you so much. So, and welcome to the next seminar and the future topical discussions. Thank you.
Okay, thanks to everybody.
Okay, bye. Thank you.